Okay. Hi, I'm Hanok from Israel. I'm leading the TRex traffic generator. Last year I presented the Stateful, and this was the model. It solves scale testing for stateful feature, like what we saw in the last presentation. Stateful feature like NFV, DPI, and it was really successful. Inside Cisco. Actually, Mellanox is using that now. And we applied for Pioneer Award and we won. It was amazing that this small project won, and this pushed the project forward from management perspective, and we had a team. Last year we didn't have a team. And after we have a team, we try to figure out what would be the next feature, and we went to the team, to the dev test team, and they want everything. They want to replace Ixia and Spirent, and it was too much, right? We cannot do everything with a team of 3 or 4 now. And one thing that I've learned from talking to the whole team, that stateful is a niche. It cannot solve everything. And we tried, to use Pareto distribution, if you know, the 20-80, to take the 20% feature that will give 80% value. And we came up with this RFC. Let's start with solving this RFC, which means to define streams, to get latency and jitter per stream, to get statistic per stream, and to have simple and very light automation API that match to the framework of the dev test that use this. And by the way, we use Python. And luckily, one of the Maciek leading the FIDO CSIT project chose TRex for the testing of EVP, and they push us forward with requirement. They are always need more requirement, and they were the first to use that. After that, there was some teams in Intel and Imperva, and Mellanox still not using stateless. So just to give an overview, what does it mean stateless? What does it mean stream? You can see the blue one, the blue stream is continuous for specific packet with a specific operation on the packet. For example, I want to change the source for this range. The green one is a burst that initiates a multi-burst. So this is a definition of a profile. You can define it in Python. I will show in a minute how you can define, but this is streams, and then you have an operation like start, stop, and many things like that. This is the relation between the object. You can have a traffic profile, and then for each profile, you can have many traffic profiles for each interface. You can have multiple streams per profile. And for each profile, for each stream, you can have a packet template, the operation to do on this packet. For example, change the packet size, change the IP, change the field, and which statistic you want to gather from this stream. Just to give an overview of the software, there is a control plane in gray, and there is the TRex server, which run on the x86 machine. Intel NICs. And you can see that everything in the gray is in Python. We chose Python 3 and .7 because it's integrated in our Cisco framework. And you can see that there is a GUI. You can have a GUI, you can have a console, like in PackageN, and you can have an API. Everything is in Python. The interaction with the server is JSON RPC over 0MQ. And there is 2 channels. One channel is request response, and another channel is async event like link down, link up, statistics was update. Using that in subscriber publisher mode, all the client, for example, if all the user can get a notification and do whatever they want. And the server processes the JSON and move it to the next slide. This is the data path. We talk to the control plane, and the data plane is most important here. You can see that the first data plane has 2 queues for each interface. We are always working in 2 interfaces because we started as a stateless, and there is 2 queues here. Usually 1 queue is for low latency. It was a challenge to configure that to the Fortville. It didn't work for a long time. and we got 1 microsecond latency. And another one is the bulk TX, just to send packets. And there is another 2 queue for receive and transmit that go to 1 core, which handle the exception packet. I will talk about that. And we are using flow director not to get all the packets. For example, if I'm doing 160 megapacket per second, I don't want to get it back. I want to get only the important packet that I want. So we're using flow director. If I add another core, you can see that there is another bulk queue. Okay? Not all the core has low latency queue. This is the messaging. There is no lock at all. So there is a one-to-many from control plane to data plane. And there is the opposite from the RX to all the other cores. Okay? Now back to the traffic profile, which is the most important thing. We are separate traffic profile. What do we want to send to the operation? What do we want to do? Do we want to start? Do we want to get statistics, etc.? So this is the low board of the traffic profile of Stateless. You can see that we are leveraging SCAPI to define the template packet. For example, here I can define UDP packets with 10x as a payload. And I can say that I want to send it in a continuous mode, and I don't specify the rate. So it will be 1 packet per second. And then I can say to the console or the API, please send it in 100 megapacket per second. And it amplifies that. Okay, this is the basic profile definition. Let's see more. If I want 3 streams in interleaving, in that case I have 10, 20, and 40 megapacket per second for each stream. I can define 3 packets template, and just change. You can see that the PPS is different between each stream, and all of them are continuous. It's really easy to define streams, start them and stop them. This is another example. It's a burst that initiates multi-burst string. Okay? So let's see how we do that. We define the SCAPI packet. We define a stream with a name S0. I can define any name. And I can say next is S1, and then I put the name on the next stream as S1. Okay? Simple, right? Field engine is the ability to create microcode inside the data path that will run really fast and will change something in the packet. For example, I want to change the size of the packet. I want to create random packet size. I want to change the toss from this range. I want to create repeatable random numbers. For example, I want to choose from 1 million number, I want to choose 100 and repeat that again and again and change the IP. So we have an engine that you can program it in Python. We compile it into the control plane, split it into the data plane, and magically it knows how many cores and do whatever. It does what you tell it. This is a scene attack. We create a range from source. We create a source port range, and then we write it to IP source and TCP port. See the program, really simple, and then I can start this profile. This is the instruction that you can create in Python. There is 2 types. One is definition of variables, and one is action on the packet, and the compiler is converting it to microcode, and it's run really, really fast. One of the challenges that we had here, as I talked before that, is that even if we have 7 core, 10 core, 11 core, whatever, the output should be like you had 1 core. So we need to split the program to whatever number of cores that it will look like to the observer that it was like 1 core. It really was a challenge. Per stream statistic means that I want statistic per stream that I define. How many packets, how many bytes, and we are doing it in hardware, in the Fortville hardware, in the other NICs we are doing it in software. It won't get that maximum performance. And you can see that it's really simple to do it. You just define another property to the stream that says what is the ID, and all this ID will go to the same counters. So we can have the ability to count. This is how it looks from the console. It's a really important feature. Another feature is latency and jitter. You can define using this property flow latency stats NID, and all of the packet of the same streams will go to the software and we will measure the latency. The accuracy that we got is about 2 microseconds and the resolution is 1 microsecond, which is really, really good even in software. Okay? There is another hardware implementation that we think about. This is how the TUI or the console looks like. You can see the maximum, the average, the window per latency, and the jitter. The performance, this is the setup that we use. We are using UCS from Cisco and Fortville NICs. You can see that there is 2 modes here. One is the VM, field engine, which is cached, we call it cached, and another is a normal, just a program that changed some field. You can see that we can reach, with 1 core, we can reach 70 megapacket per second or 35 megapacket per second for 1 core, which is really nice with all the overhead of the scheduler and the messaging that we are handling and the simplicity of the Python. In gigabit per core, iMix is more important. You can see that you can get to 100 gigabit or 50 gigabit per core, depending on the profile, which is really nice for 1 core, with all the complexity that we have. This is how the API looks like. We are connecting to the client, the name of the client. By the way, Itai wrote the client, so this is the example there. You can connect, you can reset the port, you can acquire the port because it's multi-user. You can multi-user can connect to the same machine with many ports and acquire some ports. You can add stream or can add profile, which is a Python definition. Then you can start the traffic, and you can, between the start and the wait, you can do whatever you want. You can get statistics, or you can wait to it finish. In that case, I'm amplifying all the streams to 5 megapacket per second, and I'm telling the TRex to wait to 10 seconds. Okay, because it's continuous streams, I need to run it only for 10 seconds. There are cases, by the way, that there are streams that end by itself because it's a burst of 1 million packets. And everything is handled. There is a lot of races that we solve, and we can wait, and then I can take the statistic, I can check if there was warning or events that I need to check. You see, really, really simple. One of the interesting things that we find out, that if you take this program and run it on Ixia, it takes 30 seconds the minimum. In our case, it's taking 1 millisecond to do everything, because the infrastructure is based on 0MQ and really fast. So the regression time when we moved from Ixia to TRex was scaled down to by factor 5. Okay? So the operation is really, really fast. This is an HLT, I won't talk about that. There is a standard API to talk to Ixia and Spirent, and we have in the Python a compiler that converts this messy argument to SCAPI and our native API that I've shown. Okay? We are not supporting all the HLT API. Interaction is using, there is a console. I don't have a demo here, but you can, by the way, you can connect to a DevNet and see work for yourself with TRex. It's already configured in the web. So you can, for example, start, pause, resume, stop. You can get statistics. You can control any ports. It's like an Ixia. And there is a GUI in progress, it's in beta, that you can connect, and you can see statistics, you can build, and we have a GUI builder for SCAPI that we are adding. So you can build like in SCAPI, you can build it like a tree. This is the documentation. That's it. Any question? Yes?
I have a question that, have you compared the Ixia with your TRex, such as currently we are using Ixia for the performance testing. So have you tried using Ixia and TRex just to do the comparison for the maximum throughput at the 64 bytes? Is the status same?
It's the same. The only limitation, as I saw, it's the fourth wheel limitation, that it's limited to half of the line rate in 64 bytes. Okay, it's a limitation of the fourth wheel NICs or the specific NIC. We are not limited. We have, for example, Mellanox is not limited. So if you have a Mellanox and a patch.
So how about the latency?
Latency, I told about it's one microsecond with fourth wheel. For our use cases, most of the use cases, it's enough.
Okay, thanks.
We are using hardware assist for creating low latency queues in fourth wheel, VSI, so that we'll make sure that the packets will be in low latency.
I have a question on the configuration here.
Yeah.
Yeah, so I was using TRex and I used the TRex config YAML file. So
Stateful or stateless? This is a stateless.
Stateless, yeah.
Okay.
So the number of interfaces, if I make it one, it doesn't work. So is there a limitation that we need to always have two ports connected? Because if I want to just pass traffic from one port and don't use another port, why I need to physically connect another port?
Yeah, it's a good input. We are supporting only, the minimum is 2 ports. And the reason is because we assume that the packet that you send will get from the other port to measure latency.
Okay, because in my setup, I measure latency in another server, so I don't need another connection back to it, but I need to connect another port physically, just to make it up and running.
Yes. By the way, this will be solved very near, that you don't need that all the ports will be with link in stateless. It's important. It's an open bug.
Thanks.
Thank you.
Hello? Have you tried to run TRex in a virtual machine, so both over VirtIO and over a VF interfaces?
Yes.
Then what's about the latency and the throughput? I mean, how do you sustain it?
Okay, it's run on a virtual interface like VXNet, VirtIO, and I think there is another one, E1000, and the latency are not so good there. So if you want to measure latency of 1 microsecond, which is not the solution for you.
But I was asking about a VF interface.
What?
A VF, a virtual function.
It's not supported. VF is not supported right now.
No way to make it?
What?
Is there any, I don't know the details, is there any design issues to
No, there is no design. It's just we are picking the most important feature, really small. If somebody wants to join and to add this capability, it's not a big deal, it's just a work that we need to evaluate. By the way, all the NICs and all the configuration that we are supporting, we have it in regression. So another configuration is another time in regression. So we see that we didn't break that. Yeah?
I wanted to ask you a question about your comment that the 1 microsecond is enough. There are a few, including me, who believe that 1 microsecond is not enough. XIA can do 20 nanoseconds resolution. The question I have is, well, 2 questions. One to the audience, you have any interest to get a better accuracy from traffic generators like that? And second, to you, Hanoch, or maybe the other way around, what's required to get a better accuracy?
Again?
Or is it possible to get better accuracy than 1 microsecond?
Okay.
And what's needed to do that?
Okay, so to solve the 1 microsecond limitation or barrier, there is a need to hardware accelerator. We are doing our best that can be done in software. Okay? And we are configuring the hardware for the best option for getting the 1 microsecond. For doing better than that, you need hardware assist that will put the timestamp when the packet was sent, and will put timestamp when the packet was received in the NIC itself.
Okay. So
it can be solved. It can be solved, but again, we
can you quickly comment about options? Because I just wanted to quote, if you don't mind, 2 solutions that are available that claim that better resolution than 1 microsecond using the hardware acceleration. One is onsmt.org using the FPGA, or that FPGA developed in Cambridge.
Okay, I'm talking about software on the scope of this project is work with NIC from the shelf, not on XIA. You can buy XIA as parent and get one.
Fully agree. And I think we have a presentation tomorrow from Munchen that is I've seen on the agenda.
They're using the same audio accelerator that I talked about. This, it has a limitation on the timestamp feature.
Okay. So the reason I'm asking for better resolution is actually for jitter. For jitter measurements, and we're using TRex to test virtual appliances like DPP and others, jitter matters, and believe that 1 microsecond is not enough. In fact, we know it is not enough.
Yes.
So if there are others who would like to talk, or please approach me, or just raise your hand.
By the way, the jitter is
and I would
much
like
more...
to push guys like him to actually code it.
By the way, jitter is much more accurate than 1 microsecond. Okay, only the latency is accurate by 1 microsecond, because the jitter is calculated about many samples. Okay?
Okay, so one of the scenarios we're looking at jitter measurements is actually vhost scenarios, or communication with a VM that is very sensitive to CPU jitter. And the shallower the buffer in QEMU, the bigger the impact of the non-drop rate. So that's the application we are actually after. So if anybody else is interested in measuring vhost or VM communication, you're going to hit the same problem. Thanks.
Yeah, one question. You mentioned regression here.
Yes.
Just out of curiosity, what do you use to test the TRex?
It's a lot of setups, by the way. There is all the sets of our interfaces and hardware and UCS, and it's connected usually to a router, Cisco routers, many type of router, ASR1K, if I remember, many type of ASR1K, and usually we are testing the version of the ASR1K, it kept steady. And using the ASR1K services like DPI that we developed and NAT and firewall, we check that we don't break, and all the routers report the same counters. So today we have, I think, 7 or 8 setups in parallel that work in parallel, and it takes 1 hour to finish all the regression, and it's work 24/7 without stop, and there is no even, I think there is one error, one false positive in a day, and we try to solve that. Yaroslav did a great job on that.
Okay.
So regarding the discussion about timestamping precision, I'm the developer of Moonshine that was previously mentioned, and I'll be giving a talk tomorrow. The trick basically is to make the network card believe that it's timestamping a PTP packet.
Yes,
and then
this is what I talked. Yeah, this is what I talked to. We can add this support. Just
It's actually pretty easy since DPK implemented native support for this stuff recently. So I'd really suggest it, because you really need the nanosecond precision sometimes.
Yeah. I agree. This is exactly what I sent to Maciek in email. It will be really easy to implement that in TRex now that we have all the infrastructure, all the RPC and the Python connection. I told you. Is there anyone that wants to contribute that?
All right. Thanks very much, Anna. Thank you.